Because, you know, clouds are always kind of the nicest thing outside, and, you know, they seem like they'd be kind of simple to describe. They aren't really that simple. But it led me to this idea of self-organizing criticality. So what's interesting about clouds is that you have the physics which happens locally at just above the atomic scale, which leads to a very non-local global structure and creates the cloud you see. So this behavior is complex in that clouds have many moving parts, and it's obviously one cohesive thing. But at the same time, there's no way one end of the cloud can immediately communicate with the other end of the cloud. So similar behavior is found in other complex systems. So basically, all the fractals you saw earlier, it kind of works on the same principle, which is that you have some sort of rule for determining how something develops, and it creates complexity. Stefan Wolfram has a book about, it's a huge book, you've probably seen it, A New Kind of Science, but it's about how a basic, like automatons can produce pretty much infinite complexity. So you, like he creates trees and everything else out of some basic rule sets. And, but one thing you want to understand is why the fractals aren't perfect, because, I mean, it's one thing to say they're fractals, but they aren't really fractals in the sense that although they're similar to themselves, they aren't mathematically self-similar. And so then we can think about how this happens in systems, and it turns out it happens when they're at a boundary between equilibrium and chaos. So first we'll discuss the basic physics, then how that relates to the complexity in the clouds outside. And then we can talk about the principle of self-organized criticality, and then we'll see a simple model of that. So the basic process is condensation. If you have supersaturation in the atmosphere, water will just condense, but usually you need some sort of a sea salt or something like that, which will attract the water in the air. But that can only create molecules which are so big. So because the concentration varies as 1 over r to the third, while the area or the size of your water bubble, it'll be r squared. So you end up getting this equilibrium process where for a given saturation you'll get water droplets of a certain size. So the model of cloud formation that you can get from condensation is based off these simple relations, which this is just ideal gas. This is just pressure from 2 forces, and this is adiabatic cooling. So condensation occurs, and it's a lower energy state, so heat's released into the nearby system. So the temperature goes up in the nearby system around the droplet. So the droplet rises because a change in temperature leads to a change in pressure, change in height, and then at the higher altitude, it cools down adiabatically, and then it makes its way back downwards. So then it can continue this process indefinitely, basically until your droplets achieve a maximum size. But the reason this process is useful is because the air current created by one droplet actually stimulates the air current of another droplet. So there's a diffusion relation between the droplets where their formation is coupled. So this results in a scale invariant structure, which basically means that if you look at clouds, like this could have been taken as half the sky, or it could be zoomed in nearby a much larger cloud, or pretty much anything. As long as you aren't considering something the size of the whole sky or something very small, like at the level of molecules, you can't actually tell how big these clouds are. Like you could be in an airplane, and this could be only the size of your airplane. So these researchers, Nagel and Roschke, they implemented a system, basically a discretized version of what I just described, which is just a system with that simple cycle, a few states, and many discrete lattice sites all connected going through this process. And they were actually able to create clouds that look like this in their cloud simulation. So this is actually 3D looking down through the cloud. So systems of this kind are, they're called 1/f systems because of the scale invariance, which basically means if you think of f as a frequency, if you provide a frequency, or if you provide a distance scale lambda, there will be things occurring of a frequency associated with lambda, which is just scale invariance. But it occurs in things that aren't just size. It can occur in time or maybe some other set of variables. So one example is the fjords of Norway, where if you zoom into or zoom out of the shoreline of Norway, it looks the same. So this is a common example of like a repeating pattern in nature. Another is the average temperature. So these aren't, one's the global temperature and one's the temperature in England. But what you'll see is even though there's more data here, because this is like twice as long a time period, things go on at this scale. Like you can see a gradual increase, and things go on at half the scale. And you know, if there wasn't any, if you couldn't see the numbers, then you'd have no way of knowing which is which, and that's because it's 1/f noise, basically. So like one example is if you have like pulsar data and it seems to be gradually increasing over 100 years, that might only be a fluctuation at a larger time scale. So it might not actually require any explanation. So a principle to explain this is self-organized criticality, and it's basically the idea that dynamical systems which are diffusive or related they'll be attracted to a critical state, which is right at the boundary between basically stability and chaos. So instead of things happening gradually, you'll have what's called an avalanche. So the atmosphere will change until all of a sudden you'll have like a flash cloud formation. So you don't have lots of little clouds, you get big clouds. So a model of this is a sand pile where this is the discretized version, where if you imagine you have a grid and then you place blocks of sand on this grid, and anytime the blocks get too high, you knock them down to their neighbors. So following this pattern, you can actually see avalanches where they occur with a frequency that basically avalanches of all sizes occur, but the frequency varies with the size of the avalanche. So it's not, you can expect the larger ones. You can even expect one that would take up the whole grid, but you just don't know when it'll arrive. Well, you don't know when it'll arrive, and you have to wait a characteristic time length for that size of an avalanche. So this sort of idea is important because it allows you to explain things like earthquakes or how human thoughts can occur, because there will be some small event which triggers a much larger event, kind of like a photodetector in a particle accelerator. There are a lot of examples which I can tell you about later, but I guess that'll be everything for now. Wait. What is the quantity F for clouds? The quantity F, it's just called 1 over F noise. It basically, I mean, I guess it would, let me think. So I guess it might be like cloud density or something. So basically determining how clumpy, you know, what your clumps look like. Like if you zoom out, you should be, like, when you look out at the sky, you'll see like a big cloud, but then you'll also see more small clouds. And you know, there's a relationship between the frequency of the one and the other. I don't know, does that answer your question? Sort of.
There is like a common situation that at a critical point you don't have a scale, like you don't have mass and you don't have any scale. So can this behavior of that system described as a phase transition?
Maybe a non-equilibrium phase transition. So the basic principle of self-organized criticality, which is, you know, I didn't really have time to talk about, is that nature isn't actually in equilibrium. Things happen because nature's not in equilibrium. So most things happen because things aren't in equilibrium. It's just we're in a metastable state waiting for some sort of avalanche to occur. So like any transition would be considered a non-equilibrium transition. Well, at least for the, you know, the processes which have these kinds of relationships.
Okay, and I have one more question. Can you tell more about this three-dimensional system, discrete model that form clouds?
Mm-hmm.
In which sense does it give results that look like clouds, not just any random fractal?
Well, how is it different than a fractal?
Yeah. How do we know that it gives not just a random set with
Mm-hmm.
some non-trivial characteristics, but
well, I mean, that could be a legitimate, you know, concern, which is just that there's a more general. That maybe you could say there's something more general which can generate these fractal-like patterns, but, you know, clouds are basically fractals. So the question is whether or not the condensation model can, whether you can relate that simple physics to the generation of a fractal which looks like a cloud.
Well, my question was which characteristics of a resultant fractal can tell you that it seems like a cloud, but not something more general.
You mean like, so is there like a mathematical constraint on cloudness versus just general fractalness?
Yeah. How do you distinguish?
I mean, that would be something to get into if you were going to really study it, because maybe you could make another discovery if you were to look into this further, because I don't know if anyone's done that.